Right, this is the second of two sessions on how forces act on a moving body. So last session we looked at two elements around drag force. So we looked at surface drag and we looked at form drag. And today we're going to look at a second force, which is known as lift force. Now we have seen this before, and that will become clear hopefully in a second. But essentially lift force is a force acting perpendicular to the direction of travel of an object. Okay? A force acting perpendicular to the direction of travel of an object. And we have seen this before in two particular instances. We've seen it before in parabolic flight. So our three elements of parabolic flight here, if we look at the shot put, for example, so we've had and highlighted and labelled our vertical and horizontal forces. That was just our horizontal force there, so we reached our zenith, but then we also noticed that we have a vertical force here as well. So these vertical forces are acting perpendicular to the line of travel. So the shot put is going this way, but we have vertical forces, a lift in this sense, a lift force, working perpendicular to the direction of travel. We've also seen it in our resultant forces diagrams. So when we've looked at the long jumper, for example, here is our perpendicular force to the direction of travel. So again, we have seen it before, so worth making that link. However, what we're going to look at in particular when it comes to lift force today is actually how we can manipulate lift force to provide a better performance, okay, improved performance. And in particular, the one thing that I do want you to lead to this session with is an understanding of the Bernoulli principle. Okay, so the Bernoulli principle is central to what this session is going to be about. And the Bernoulli principle essentially looks at ways in which lift can be manipulated to allow objects to travel further, particularly in the air, or to move faster. Okay, to travel further or to move faster. We're going to start with a very simple kind of explanation, a simple example around the discus. Okay, so anybody who's seen a discus will notice it's kind of, I'm going to try and draw it, but I'm never successful in these things. But imagine a discus in flight. We know that the release height is higher than the landing height, so we know then that a release height is going to be less than 45 degrees. I'll explain that a little bit more in a second. I can go into a bit more detail now, even though we understand that and we know that, actually, to explain why. I hope this works. So a discus kind of looks like that, kind of bit of a pasty really, but anyway, it will help. Perhaps a little bit shallow as well, but it's just been released. There's our direction of travel. So down here is our direction of travel. You can't see that. That's our direction of travel. Okay. Now, it's discus that is travelling this way. So what we have is we have air resistance. We have it travelling in through gases. Okay. So at this point here, that airflow is obviously meeting it and moving around the discus. Over the top. Now, what I'm hoping you might recognise through this drawing is the air that's passing over the top of the discus is actually having to travel further than the air travelling beneath the discus. All right. Now, if air needs to travel further, it goes faster. Okay, so the air travels faster where it's got furthest to go around an object. So we're just going to highlight that through this use of a kind of double arrows. So the air moving over the discus is travelling quite fast. It's certainly travelling faster than the air underneath the discus, simply because this air doesn't have so far to go. Now, the result of that is that the air that's moving faster, the air that has to go further, actually now has a lower pressure than the air that's moving underneath, okay, the air that's not moving quite so fast. And as we know about pressure, and as we know about air pressure, and we go all the way back to mechanics of breathing, if you want, in terms of breathing in passively, is that higher pressure air wants to move into areas of low pressure. So to do that, it's got to move upwards, okay? And by doing so, it creates, on the discus, lift. And that's no different to I'm scribbling all over the place now, but that's no different to an airplane wing. It's kind of like that. Okay, I'm sure there's a bit more nuance than that, but it's kind of like that. If you're looking at a cross section of a wing, and air that's hitting it here, actually over the top, travels further than the air going underneath. Okay, which means there's a lower pressure above the wing, a higher pressure below the wing, and therefore the plane is lifted. We create lift. Okay. So that happens on a discus, and if we just think back to the idea of our release, so an argument's saying, let's be really specific and say 43 degrees. Well, at 43 degrees, what we have now, because our release height is higher than our landing height, if I release it higher than that, so if I were to release it, and I'm now getting into real danger of just drawing too much on here now, but I might as well do it. If I've got a 45-degree angle here, I've got air resistance hitting quite a large cross-section area there. You know, when you think about a discus, you know, it's wider than the palm of my hand, actually coming in and hitting air, we already know that air resistance or objects with a greater cross-section area experience greater air resistance. So actually throwing it at 45 degrees or below will actually incur quite a lot of air resistance and no lift. We want to get underneath it. I want to give an opportunity for air to get underneath it, high pressure air to get underneath it to lift. So therefore, it is at less than 45 degrees, which means now I've got my leading edge coming through. Talk about form drag. I've got my leading edge at this point here, rather than this being a leading edge. I have a more pointed leading edge, a more spherical leading edge, and then at that point I'm allowing air to move faster over the top, slower underneath, and create lift. And now the discus can travel further by manipulating that lift force. But what's important to recognise is that actually lift force doesn't just act in one direction. And I know we've used, I'm just going to rub this off if you don't mind, but I know we've talked about the word lift force, but actually lift force can act the other way. So in particular, the example wants you to have an understanding of how lift force can act in the opposite direction with cyclists, with speed skiers, and with racing cars. And in particular, we're going to look at kind of Formula One. And if we think of Formula One, and we think of those huge rear spoilers, there's a number of different spoilers, a number of kind of air deflectors on a Formula One car. But if we think of the rear spoiler kind of looks a bit like that. Okay? There's nothing here, it doesn't come down here or anything like that. It kind of sits there, out a bit pointed, and it will come round here to that point there. So it sits on the back of the car like that. So what's the reason for having that spoiler there? Well, let's look at the airflow again. So the airflow that goes over the spoiler, over the top. Okay, that's the top part. Now remember what we had with the discus and what the air was doing on the top. Now let's think about the spoiler. Now let's just think what's happening here. So now the air underneath the spoiler is now actually having to travel further than the air on top. Okay, so the air underneath is now travelling further. Therefore, it's travelling faster. I'm not going to do all of these because it'll take minutes, but I'll just run it. Which means the air on top is travelling more slowly. Now, no prizes for guessing then that actually there's higher pressure above the spoiler and lower pressure underneath the spoiler. So instead of creating lift or a positive lift, actually that lift force is pushing down, pushing the car into the track. So we could call that negative lift, or we could call it downforce. Okay. Now what does that mean to the car? Well, it means now that it can move faster, particularly through corners. It means that the car is almost being jammed into the track. It provides greater grip, it provides greater stability, and now allows that Formula One car to move at faster speeds. So there's less braking going into corners, it allows them to accelerate quicker into the straights, and therefore create faster lap times. So that's what it means for those. Now think about it also for the cyclists and the speed skiers. So when you look at your booklets, have a consideration about the position that they're in. Okay, we have looked at surface drag and we have looked at form drag, but now you're looking at lift force, that manipulation of forces acting on a body as it's moving. Why do they position themselves in such a way in terms of the cyclist? Why do speed skiers position themselves in certain ways in order to make or take advantage of that downforce? So now have a look at your worksheets and let's see how you get on.